morphology and porology. Okay. Now, the one that happens inside of a single organism, I think that's the people. You guys can check it out. Paralogy, which means duplication of the gene or the protein, but inside of the same species. Okay? Now, there's a different kind that happens when through speciation, and so we have one species. And through speciation, I don't know what caused this, some mountain range or some river, split the population. Now you have two populations. They no longer interbreed, and through drift or different selection, they become different. And what used to be one protein becomes two that are similar, very similar, and they've retained the similarity in sequence, they've retained similarity in structure, they've retained similarity in function. And so if you, let's say, had studied this particular protein in this species, these might be, I don't know, yeast, and over here we have humans. That seems like a long evolutionary distance, but actually not at all far-fetched in terms of what advantages people are able to gain from sequence comparison. So you have a protein in yeast, and you have what you can identify as essentially the same protein in humans. Let's say because of sufficient sequence similarity, then the function and the structure of this protein is likely to be similar in important ways to the structure and function of this one. So this is a way of leveraging knowledge. If you've intensely studied the yeast proteins, and you can do all kinds of experiments, you can do knockout experiments and see what happens to the yeast, you can breed them, or let's say fruit flies. You can set up crosses and so on. You can learn all kinds of things about, you can just create mutations, feed them all kinds of awful stuff that create genetic mutations and see what happens, and then study where that mutation actually occurred. So you learn a lot in these model organisms that you can study experimentally that you couldn't study in humans for a variety of ethical and technological reasons. And yet, when you see a protein sequence that's similar in yeast or similar in fruit fly, to what is in humans, an awful lot of what you learned in here about the biology applies here as well. And the reason in this picture is because of the common descent. So these are orthologous, maybe spelled this way. It doesn't matter. We're not going to use these words. I don't like the big words, but just in case you've ever seen them before, this kind of duplication, I believe, is called orthologous, and this is paralogous. Okay, so let me just, in fact, give you a quote. This is a quote from 1995. This is a Nobel Prize winner who was talking about earlier work, maybe 20 years earlier. He said, "We didn't know it at the time. We found that everything in life is so similar that the same genes that work in flies are the ones that work in humans." Okay, so I've actually seen another quote which talked about humans as just great big fruit flies without wings. Yeah, and how you feel about that? Or the other one is that mice are just furry little people, because mice and humans are very similar at these levels as well. All right, so the first rule of biosequence analysis is that sequence similarity implies functional or structural similarity. And the basic reason, one basic reason for it is history. Either this kind of duplication with modification or this kind of duplication with modification. But either way, the moral is the same. And when you find two different sequences that are highly similar, it's a good bet that the things you learned about one apply to the other. All right. Another quote, studies on yeast are remarkable predictors of the human system. Another quote, again, these are quotes from about 5 years ago when all of this started to become crystallized, that how incredibly similar different organisms were. This is from a paper called Flies Invade Human Genetics. And again, how you were leveraging information about fruit flies to the study of humans. The quote is back then, and they were talking about the 1980s. When a gene was discovered in Drosophila that had a homologue in a human, it was like, wow. Now a researcher feels apologetic if there isn't a homology observed. Okay, so there's another word that we will use, homology or homologue or homologous. Now, a proper definition of the word homologous, two sequences are homologous, means that they share a common ancestry, that they were derived either in this process or in this process. Well, I mean, if you just sort of buy into the basic picture of evolution, everything ultimately has a common ancestor. So it's not quite enough to say that two sequences are homologous if they have a common ancestor or common ancestry. It's implied, really, that that common ancestry was recent enough to explain why the two sequences are so similar. So similarity and homology are two concepts that often get confused with each other. People oftentimes talk about what's the level of homology of two sequences. That is a complete misuse of the proper definition of that word in its proper sense. So we're going to be very careful in this class and talk about the similarity between sequences, and we'll have precise definitions of what it means for two sequences to be similar. When we talk about homology, that's saying that the similarity came because there was a common ancestry. So homology means common ancestry, common origin. And you use similarity as evidence for homology. Okay? You don't discover homology, you don't discover the level of homology, you discover the level of similarity and then use that to infer that there was homology. Okay, so this is one explanation for the first fact. There is another explanation for the first fact. Anybody care to toss one out? Is two sequences that are highly similar, have highly similar in sequence, are highly similar in function. We're explaining that by history. What's another possibility?
Maybe a similar sequence of amino acid performing into the same structure.
Okay, and you're going to say something back?
No, I was just going to say more along the lines of convergent evolution, where it will necessitate the...
Okay, so there are two ideas here that may actually, in the end, be the same. One was that you have certain amino acids in particular places because we have to. Okay, and the other one is convergent evolution, which is a little bit different. I think we'll try to make it plausible. We'll come back to this one. Convergent evolution is that two sequences didn't have common ancestry, or it's not just sequences, but two features, like wings or flight, are not similar because they have common ancestry, but are similar because they just happen to both evolve that, right, for whatever reason. So actually, I was at the library yesterday just flipping through papers and saw one on white pyramids are the same as, and I don't remember what the same as part was, but the pyramids, the claim that was made was that pyramids that you find throughout the world, in the ancient world, were independently invented. It wasn't that pyramids were built in one part of the world and then people elsewhere learned about them and copied them, but rather pyramids were the invention of humans in many different populations. And similarly, I think that flight is believed to have originated independently several times. So there can be convergence, there can be the similar features that are not because of common ancestry. Okay? But in my limited understanding of these things, convergence is more likely, or at least more plausible, in sort of high-order features such as flight. Okay? But at the molecular level, it seems very unlikely that two sequences just evolved totally independently to become identical in two separate instances if the sequence was fairly random. There's a lot of different changes are possible for the same function. So the other idea, and why this makes convergence more plausible, is the idea that for a particular function, you have to have a particular series of amino acids or particular nucleotides at particular positions. Otherwise, it just won't have that function. So this is nicely summarized as chance versus necessity. And there's a famous book, almost that title, Chance and Necessity, that really focuses on just this issue. Do you have similarity because of common ancestry, in some sense chance, or is it necessary to make that organism work the way it does? Generally speaking, today, I've erased this, but back here where we had biomodels and simplifications and rules, the general assumption is that similarity is due to common ancestry, is because of common ancestry. But the kind of necessity that says you have to have this particular amino acid at this position or else it's just not going to work, no matter what else is going on, that doesn't explain a great portion of the similarity, even though it is clinically very important. I mentioned this last time, there are particular positions in particular molecules where when you make a change, it has very serious consequences. So if you imagine an evolutionary system that's where two molecules that are similar are sort of drifting apart, that mutation is not going to happen there. But otherwise, the constraint of nature is not generally believed that the nature is so constraining today that similarity is due to necessity, but more often now due to chance, meaning history. Okay. All right. So, given the first fact, we have the following quote. Today, the most powerful methods for inferring the biological function of a gene, or the protein it encodes, is by sequence similarity searching on protein or DNA sequence databases. Because once you've learned a lot of different sequences and once you know about them, you should catalog them, which is what people have done. They've built databases which list all of the DNA and protein sequences that they know about and what they know about them. You've all probably had some exposure to these databases, and that's why you're probably interested in this area. With the development of rapid methods for sequence comparison, both with heuristic algorithms and powerful parallel computers, discoveries based solely on sequence homology have become routine. In a sense, this is an example of the misuse of the word homology. He should have said sequence similarity have become routine. But you see the point. Similar quote, determining function for a sequence is a matter of tremendous complexity, requiring biological experiments of the highest order of creativity. Nevertheless, with only DNA sequence, it is possible to execute a computer-based algorithm comparing the sequence to a database of previously characterized genes. In about 50% of the cases, such a mechanical comparison will indicate a sufficient degree of similarity to suggest a putative enzymatic or structural function that might be possessed by the unknown gene. I'm just saying this is valuable in today's biology. Again, these quotes come from the mid-1990s when people were really starting to buy into that view. And you've probably all grown up with that and wondering why I'm belaboring something that's so obvious. I could have gone back to the 1980s and 1970s to find quotes from people who not only didn't believe such things would be possible, or even earlier, didn't believe that molecular biology, the kind of things that people do in molecular biology today, were going to work at all. Mixing and matching of genes. Or most of the view was, you take a gene out of one organism and stick it in another organism, you're just going to kill the thing. Or where you take gene splicing to create some different gene that was already there is, again, mostly just going to kill the organism. So the kind of cutting and pasting that molecular biologists started doing 20 and 30 years ago was, in some sense, considered laughable to, I don't know if anybody, but mostly the sort of more entrenched biochemists who just didn't believe that kind of stuff made any sense whatsoever. But it did in molecular biology, and it comes back to the same thing here, a tremendous level of similarity that exists in different organisms, in different sequences, and what you can get from that. Now, I want to make a point before I move on to something that's technical. Once we get into technical stuff, we're probably never going to come back to this level of philosophy, but we will refer to this. The first fact of biosequence analysis is what I consider pays all the bills. I mentioned that before. But you have to be careful not to confuse this with the converse statement. Okay? This says when you have high similarity, high sequence similarity usually implies significant functional, structure, or historical similarity, or historical relationship. Okay? So this is, if you just want to think of this as a logical statement, high similarity implies, so this is statement A, significant functional, structural, historical similarity. That's B. So we have a statement here, A implies B. Okay? What's the converse statement? B implies A, right? Okay. But what does it mean in terms of the actual meaning here is that functional, structural, or historical similarity implies sequence similarity. Okay? That's the converse of this fact. That's not true. Or at least it's not a rule that people have bought into. There's tons of empirical evidence that that's just not true. This arrow goes one direction. Okay? It would be lovely if it was true. It would mean that all you ever had to do was study sequence similarity, because anytime two sequences were different, were highly different, then they would have significant differences. Okay? Unfortunately, that's not true. I mean, it would just trivialize the study of biology. As powerful as the first fact is, biology is still not trivial. If the arrow went the other way, it would make things very, very simple. So let me give you a quote here. Fred Cohen says, similar sequences yield similar structures. That's our first fact. But quite distinct sequences can produce remarkably similar structures. Okay? So that's the converse statement. Unfortunately, it's not true. Well, unfortunately for the study of biology, it's not true. Fortunately for bioinformatics, it's not true, because it means that you have to develop lots of other tools and other methods for studying the converse direction, the opposite direction, when you know that various molecules are structurally similar, when you know that they're functionally similar, historically similar, but they don't look alike. They're not obviously similar in sequence. Then you have to try to figure out what portions of them are similar, in what way are they similar. Okay? So we have two parts of bioinformatics. We have the easy part that pays all the bills, which is this direction. When you see two sequences are similar, sequence similarity, you can infer things about them. But when you know two things are functionally similar, but they don't look alike, but you still think somehow there's some similarities in there that just are not obvious, you need more powerful tools to find what the similarities are. That's working the other direction, and that's a great deal of tools that we'll look at as well in this class that people are working on. That direction is much more of a research direction in bioinformatics. Okay, so I want to introduce. Okay, so I've tried to motivate why we're interested in similarity of sequences. Now I want to try to start by saying how we try to make that precise, what the notion is. No. Can I figure out how to use this? I've had about 5 lessons on this, I still can't figure it out. If I'm going to zoom in. I can fill the whole screen. Is this readable? No, it's not, because there's nothing on there. Yeah. I want it to fill the whole screen. Zoom in far. All right, that may be the best I can do. Is that readable? Well, all right, I'll put that up on the board as well. So when we say that two sequences are similar, ultimately we have to have a very clear definition of what we mean by similarity. That's like a mathematical model. Remember, back in this whole chain of reasoning, we had a mathematical model. And then we have an algorithmic question, or algorithmic problem. If we have a clean mathematical definition of what it means for two sequences to be similar, can we compute that level of similarity efficiently when we're given two sequences? How do we do it? What's the algorithm that we use to compute that similarity? So, what we mean is the following. We take two sequences. So this is similarity. This will give you a definition of similarity. So I have a sequence S1 and a sequence S2. Now they may actually be of different lengths. One may be of length n, and one is length m. So two different lengths. But what you're permitted to do is you insert spaces into or at the ends of each sequence, each of S1 and S2. So you insert spaces. So maybe I'll insert a space here, which will move things over a little bit. insert a space here, moves this over even more. These themselves are spaces. This is a space. After you insert the spaces, the lengths of the two sequences should be the same. Okay? So you insert spaces so that the resulting lengths of S1, I call it bar because it's changed now. You put spaces in there. It's not exactly the same sequence it was before. If you consider a space, let's say, to be a character, the new sequence is different. But the lengths of S1 bar and S2 bar are the same. Because they're the same, now you can correspond the first character in one to the first character in the other, second character in one to the second character in the other. So there's a one-to-one correspondence between the characters in one sequence and the other. Some of those characters, let's say, may be spaces. Now, hopefully you can see, can you read this in the overhead? Yeah, okay. So here I have two sequences. The top one is AA. Let me see if I just focus in on this one. Okay. The top sequence originally was AACTACT. Now there's a space represented by a little dash. And there's another space, there are two spaces at the end. But the second sequence below it has two spaces, CT, CC, and so on. Okay? Although they didn't, the way it's actually displayed isn't very pretty, the two sequences are of the same length. And so there is a one-to-one correspondence. There's a first character, second character, and so on. And when we correspond a character to its opposite character, I put a dash there. If that's a space, if I have a character opposite a space. And I have a straight line if the two characters are the same, and that's called a match. And then I have a dashed, a little dotted line here if the two characters are different, and that's called a mismatch. And the terminology is not terribly surprising. Space, match, mismatch. Okay? So, putting spaces in here so the two resulting sequences are the same length, that's called an alignment of S1 and S2. And I think that's where I'll end. This definition will start next time, building on the definition of alignment, and it will tell us ultimately the definition of similarity between two sequences. Last time I started talking technically about how we compare sequences, how we define two sequences to be similar. But I wanted to step back just a little bit because there's something else in the paper today. This is New York Times, but it was actually based on a science article that just came out. A group just announced that they've sequenced, at least have a rough sequence of the rice genome. And there were some nice quotes in this article in New York Times that really exactly illustrate the kind of things that I was talking about in the last lecture. So let me just read some of these to you. Plant geneticists have discovered that the genomes of many major cereal crops are similar to that of rice and have their genes arranged in much the same order. Actually, I'll show you a picture of that in a minute. Although the rice genome is more compact and was easier to decode. Rice is the Rosetta Stone of the cereals. Once researchers have found an important gene in rice, they can look for its counterpart in other crop plants and insert the rice gene itself, since the genes of all these crops are thought to be largely interchangeable. So that interchangeability, the similarity of function, was something we talked about last time, and it's sort of taken today as one of the simplifying statements about molecular biology, but really was not known 25 years ago, and it was one of the surprises. The decoding of the rice genome is expected to unlock the treasure trove of genetic information in world seed banks, because with markers for any gene of interest, readers can now quickly search for a better version of any rice gene or for the counterpart gene in other crops. So again, it's that same idea. And let me show you what this looks like, this crop circle. If we can have the camera on here, please. This is from a science article in 1997. Actually, I think this article is in our the list of references, but unfortunately, when you access it that way, they omitted this circle. So what this circle illustrates is, in the inside here, I think it's rice is the smallest of all these genomes, and there's an ordering of important genes that are illustrated there, and each of the concentric circles around it is some other grain. They have foxtail millet, sugarcane, sorghum, maize, etc., up to oats. And there's really a nice circular correspondence between the equivalent genes in each of these grains. So if you start in the middle here and you recognize a gene in rice, and you just go straight out, you'll pretty much hit the equivalent gene in these other grains. So the linear order, although they've drawn this in a circle, the linear order of these genes in these different organisms, these different grains, has been preserved. The genomes of these different grains are very, very different. Wheat, I don't know whether they're showing wheat on the outside here or not, but wheat is enormous in comparison to rice, and yet pretty much has the same complement of genes. So I'm going to turn the camera back, because here it shows that wheat has a genome size of 16 billion bases. If I'm right about that. Yes. So that's it's much bigger than humans, about more than 5 times bigger than humans just in terms of the overall size of the genome, the number of nucleotides. Whereas rice is 430 million bases. So if humans are about 3 billion, you can do the arithmetic. But yet, the rice genome and the wheat genome, in terms of the genes, they're not only do they have pretty much the same complement of genes and then they're interchangeable, but the linear ordering of them has remained the same. So when you study rice, nice and compact genome, what you learn about it is very applicable to the other grains, and that's why we catalog and make it easily accessible. Everything was learned about rice or one particular grain, and then when you have something you try to learn about another grain, you can look it up. If you have a gene sequence for another grain, and you find what's similar in rice, where you've studied that intensely, then you know a lot about the gene that you're trying to understand. Okay, so that's all by way of review, really, about what we were talking about last time, the importance and utility of sequence comparison in genomics, and therefore that sets the stage for what bioinformatics is principally concerned about. So last time we were beginning a formal definition of string similarity. What does it really mean if we talk about two sequences or two strings being similar? And how will we compute that? And we started really with another definition. I don't think I had time to write it up as a definition, but I gave an example. And now I want to do this alignment of two sequences, S1 and S2. And what we mean by that is that we insert spaces into or in front or at the ends of S1 and S2 so that the resulting length is the same. Lengths are the same. And then, because the lengths are the same, you can talk about the two characters in position 1 and the two characters in position 2. In any particular position, there might be a space, or it might be one of the original characters. It might be two original characters opposite each other, or it might be a character opposite a space. And then, that's an alignment. Okay? Some alignments are good, some alignments are bad. We'll talk about what it means to be good or bad. What's the quality of an alignment? What's the value of an alignment? But right now, an alignment is just, you take the two sequences, you stick in spaces where you like, so that the resulting lengths are the same, and that is an alignment of sequence S1 and sequence S2. So let me give you an example of one. Let's try this one. QAC space DB D and QAW X space B space. Okay? So these are two sequences which originally had different lengths. This one had length 6 and this one had length 5. But when I inserted spaces or put spaces at the end, the two lengths are the same, and therefore I can talk about this is the first position, second position, and so on. Now in each position, you can look at it and see whether it's a match or a mismatch or a position that has a space. So this is a match because the two characters that are opposite each other are the same. This is also a match. This is a mismatch because the two characters are different. And this one is a space. Now generally, or character opposite of space, generally in the alignment of two sequences, we don't permit or encourage one space to be opposite another space. So if you have an alignment that's like that, you can just get rid of those two spaces. When we talk later about multiple alignment, aligning more than two sequences at a time, we can have situations, in fact it's quite common and valuable to have situations where we'll have a space opposite another space, but there won't be spaces in that position in all of the sequences. There'll be at least one sequence that has a real character in that position. So for every position, there's at least one real character, they're not all spaces. All right, so now we can talk about the value of this alignment. This is a particular alignment, and its value, whether it's a good alignment or bad alignment. Now, before I tell you one way we're going to formalize whether an alignment is good or bad, you should try to remember what is the objective here. Okay? Going back to the corpus of biological data, that is, people have learned things about the rice genome, the wheat genome, and so on. Out of that came this general observation that we talked about last time, that similar molecular sequences tend to have similar function or structure or history, and therefore you want a way of formalizing the notion of similarity. So where are we in this chain of reasoning? The chain of reasoning had the biological data, the biological simplification, or the rule that similar sequences give similar structure. Then we had sort of we're at the mathematical stage now of saying, let's try to define what we mean by similarity in a very precise mathematical way. But we want that definition to reflect the biology. The definition has to be meaningful. It has to try to be such that when we actually compute alignments that demonstrate the similarity of the two sequences, it reflects the underlying biology. So what is the underlying biology that creates differences in sequences? And here we have things that are identical. That's probably a good thing to try to line them up. If they're identical and you can line up a lot of them, that's a way of saying these two sequences are pretty similar. They haven't changed a whole lot. But what causes a mismatch? Why do we even permit an alignment to have a mismatch? What does it mean biologically?
Mutation.
It's what?
Mutation.
That's a mutation. Okay, if we think procedurally or historically, a mutation. And in particular, this is what's called a point mutation. because it's happening in a single nucleotide. Okay, so that is something that's common in the evolution of molecular sequences. That whether it's DNA or protein, you'll have single residues, single positions, which will mutate, which will change over time from one residue to another. Okay, so it's acceptable to have that as a concept, a mismatch, and to allow that in an alignment. What's a space?
Insertion and deletion?
Yeah, another thing that happens over time molecularly is either the insertion. You take some sequence that existed at one point in time, and then it can happen that there is an actual insertion of new material. Let's say DNA is the easiest to think about. New DNA into that sequence, which that particular sequence becomes common, and you later sample it. So you have these two sequences, the ancestral and the current, or you have two that are current that derive from a single ancestor. But the point is that the difference between what you have today and what was ancestral could have occurred by the insertion of materials. There are lots of molecular mechanisms that cause that. Anybody want to throw out at least 17? Just list a few. Try one first.
What is the question again?
What causes insertion of new DNA?
Like transformation.
Transformation. Okay, that's just a word. What does it mean?
It's when like a bacteria gets stopped or something.
Infection of virus.
Is that what?
Infection of virus.
Okay, so viral infections, bacterial. I'm not sure what the word is there, but bacterial transfer of DNA also occurs. Anybody heard gene conversion? Slippage in replication and so on, where additional the replication isn't exact, but there's an additional insertion of material from one copy into another, and so on. You really could easily, and certainly there are articles that do this, list 17 or 20 different molecular mechanisms that are known to cause insertion of new DNA. And if you talk at the protein level, the story would be a little bit different. Of course, it's all happening at the DNA level, but where you end up seeing two proteins, one is ancestral and the other is more current, and one has a region in it that the other doesn't. There are various explanations for that as well. What about the opposite way? What's another way that spaces get generated? Historically, deletion. Right. So you have some sequence. And again, it's hard to see the ancestral sequence, although not always impossible. We're talking about viruses. They mutate rapidly enough that you can actually see historically a virus and then some of its derivatives. But it's easiest to think about this historically. So you have a sequence, imagine you have a ancestral sequence, and then there's some deletion of some intervals of that. Well, that also occurs. Some of those are the opposite. For example, the gene conversion, where some material is moved from one to the other, then the one that had it is perhaps missing it. There's some other mechanisms that excise DNA. And in fact, there's a big question, really, of which is more common, insertion or deletion. If you were to look at if you did have the ancestral sequence and you have the current sequence, and they're different, is it because the modern sequence has actually had additional sequence inserted, or did they lose? Okay. So there are a lot of questions like that. For example, there's a basic question of whether introns were early or late. In other words, we have in eukaryotes, I'm sure everybody knows this, in a gene, you have regions, or if you don't know this, it's important that you do. In a eukaryotic gene, typically, you'll have alternating intervals, what we call exons, interrupted by introns, actually interrupted as part of the origin of this word intron. And actually, the introns are generally much bigger than the exons. I'm just drawing this out of scale. And you may have 7 or 8 of them in a typical gene. And then what happens in transcription, all of this gets transcribed, but later the introns get removed, the exons get concatenated, and that becomes the transcript that's used to produce the protein that this gene codes for. So there's a question, a historical question of, and so eukaryotes have this, prokaryotes do not have the introns typically. So there's a question of, what's the history of this change? Was it that introns became inserted, or the genome of eukaryotes came to have introns that prokaryotes don't? Or was it that prokaryotes had them and they lost them somehow? And of course, that's unresolvable in a way. People argue about it one way or the other. But my point is just to say that there is insertion and there's deletion, and in the transformation of molecular sequences, many mechanisms for that, and plenty of controversy about some of them. So when we talk about two sequences being similar, it's the matches that tend to suggest similarity. Mismatches argue against similarity. But the ability to put in spaces here, allows you to fiddle with these sequences so that you can get matches and avoid mismatches. And the reason that's permitted, the reason that makes sense, any definition of similarity here, is because in nature there really is insertion and deletion. We'll want ultimately to have our definitions model the biological processes properly, so that, for example, if yes, there is insertion and deletion, but we shouldn't allow just enormous amounts of it, just so we can get some matches and avoid some mismatches. Or maybe it's biologically right to allow as many as we want, and then in order to get many matches. But ultimately, the definition of similarity has to model the basic biological reality that you're trying to model, that you're trying to capture in your model. So the simplest model right now is the value of this alignment is just going to be the number of matches minus number of mismatches minus the number of spaces. And we're going to embellish this. This is called an objective function. or a value function. We're going to embellish this to try to better match the biology throughout the quarter. But right now, we'll just start with this very simple value or measure of the goodness of this alignment. So in this example, we have 1 match, 2, 3 matches. We have 2 mismatches. And we have 3 spaces. So it's -2. So the value of this particular alignment is -2. Okay? Now, did I do that right? Okay. 1, 2, 3 matches. Only 1 mismatch. Thank you. Okay. So we'll have to think about, I want you to already begin thinking about, is this a good reflection of the biology? To talk about the value of this alignment just in this simplistic way. Number of matches minus number of mismatches minus number of spaces. At least I think the signs go the right way. That this is a positive thing. If you have lots of matches, if you can insert and move around the spaces so that you get lots of matches, that somehow emphasizes that these things are similar, just in the colloquial sense. Mismatches certainly work the opposite way. And it's these spaces really which are the kind of thing that may not be intuitive to you yet, because with lots of spaces in there, you can make a lot of matches and avoid a lot of mismatches. So is this really the right way of handling spaces, just to subtract off them? Have you captured properly the biology? It's probably an empirical question and probably differs a great deal by the particular application. Whether the way you line things up here according to this value properly reflected the way you think 2 sequences really relate to each other. Because working backwards, when I have an alignment here, you'd say, well, this was a mutation, this was either an insertion or a deletion. I don't know what it is. And that, by the way, explains the typical term for a space that you'll see in biology literature, or bioinformatics literature. An indel is just another word will mean for space. And this means either insertion or deletion. I don't know which it was. When you look at it in alignment, it's a space. But historically, it was either insertion or deletion. All right. So that's the value at the moment we're going to take for a particular alignment. With that, we can define what it means. What we mean by string similarity, or the first definition of string similarity, the simplest one, which is this. It's the maximum possible value, string similarity of sequences S1 and S2. The maximum possible value of any alignment of S1 and S2. So this was one particular alignment of these 2 sequences. There are many others. In fact, we'll count a little bit later. We'll look at how many different alignments there are. But this was just one particular one, and it had a particular value, -1. But if we say that a large value here tends to suggest that these are similar, and a small value tends to suggest that they're not very similar, then this definition makes intuitive sense. But if we want to define precisely what the similarity is of 2 sequences, it's obtained from the alignment that gives us the largest possible value. Okay? And so this is what I would say is the mathematical model of similarity. This, again, emphasizing where we are in this chain of reasoning. Just an abstract definition, really. And again, you have to ask yourself whether this mathematical model properly captures the biology that you're interested in. If you have several sequences and you look at each pair of them under this definition, assuming we know how to compute this, but we'll get to that in a moment, and you look at the numbers that come out, will it be such that when you look at those sequences, you say, yes, these 2 that have the large number I think really are highly similar, so this was a good definition, and the 2 that have a low number really are not very biologically related or evolutionarily related. You want this definition to have that property. And this is just very, very common what people will do if you have hundreds of sequences and you have a program that can compute this. You'll compute this for each pair, and then you'll say the ones with the large number are pretty evolutionarily related or related in some important biological way, and the ones with a small number are not. And then you'll group together the ones that all have a large number together and say that's some kind of common family, and that exercise is called clustering. So this is at the heart of, such a definition is at the heart of a huge amount of things that we do in bioinformatics. Database lookups are based on such definitions. The numerical data that's used in building phylogenetic trees is based on such definitions. The clustering I just mentioned is based on such definitions. So this kind of simplistic model, that we will embellish it, we'll make it more relevant, is at the heart probably of the majority of what's done in sequence-oriented bioinformatics. And finding a similar kind of, analogous kind of definition for things like three-dimensional structure or regulatory networks and so on is what people try to do. So they try to follow this paradigm for things other than sequences. So we have to understand this, and we have to also come to see whether we believe it made sense. All right, so this is the mathematical model of similarity. The next stage in that chain of reasoning, the algorithmic problem. How do we compute efficiently the similarity of two sequences? So the mathematical model gives you the what. This is what we want to compute. The algorithmic problem is the how. How do you actually do that? So what I like to do whenever I'm faced initially with a how question or an algorithmic question is, first of all, think fairly naively, brute force. How would you just do it if there were no constraints of efficiency? All you try to do is come up with some simple method. The way I like to think about that is somebody comes in that door with, in one hand, $1 million, and the other hand, a gun, and they say, you have 5 minutes to think of a method to solve this, and get programmed. If you do it, you get the $1 million. If you don't do it, I shoot you. So you don't have time to be clever. And cleverness takes time to think things through. You just have to do something that your fingers can move really quickly and write the program. They didn't say you actually had to get the program had to finish in 5 minutes. It's just you had to finish writing the program for that problem. So what is the most straightforward way of trying to compute the similarity of two sequences? We have a definition of similarity. The definition of similarity is the maximum possible value. We have a definition of value. Okay? Given an alignment, we can compute the value. The similarity is the maximum value over all possible alignments. So the brute force thing to do is to try to generate all the alignments. Just write some program that will generate all the alignments, compute the value of each one as you've generated it, keep track of what the best one is, and when it's finished, you'll have the value, and you'll also, if you've kept the appropriate information, you'll have what that particular alignment is as well. Okay? Now, what does it take to generate all possible alignments? I mean, an alignment is defined by where you put the spaces in. Okay? So you really only have to choose at every particular position whether you're going to put a space in there and how many. Okay? You certainly are not going to put in, we said you're not going to have two spaces opposite each other, so the total number of spaces you put in is only going to be, at most, as many characters as there are in the other sequence. Okay? So I'm just outlining how you would start writing a program to do this. It would probably have several nested loops. One which would have a loop talking about how many total spaces you're going to put in there, another loop that's going to talk about where you put these spaces in, another loop that will then go through the two sequences as they're aligned and compute the value and so on. Probably, those of you who've taken the prerequisite courses for this one and actually have some programming experience, you could probably write a 3-loop program that would do this when any sequence comes in. And it may actually be worthwhile later, probably not now, but when you know enough Perl to try to write that program, give yourself 5 minutes to write it, then after 3 or 4 hours, it'll be done. I sometimes do that in just a sec. I'm going to take 5 minutes on this program max, and then, again, about 4 hours, it's sort of done. All right, but that's one approach. I'm not showing you in detail because it's not the approach we're going to emphasize. Because, we'll see in a minute, there are a lot of different alignments. There are so many different alignments that approach will not work. People like to think naively that computers are very fast. They like to think computers are big or computers are smart. But those 3 assumptions, if you're in computer science, we start from just the opposite. And all of the problems in computer science are based on the fact that computers are really teeny. They don't know very much at all. They're very slow, and they're very stupid. They only do very simple mechanical things. And almost all of computer science is based on trying to get around those 3 basic realities, even though a lot of people think just the opposite. And of course, compared to some of the things, computers are big, fast, and smart. But compared to what we want them to do, it's appropriate to think exactly the opposite. And in this problem in particular, straight brute force enumeration of all the alignments would be absolutely out of the question. I don't know how many ages of the universe it would take for 2 sequences, well, we'll figure this out in a minute, for 2 sequences of lengths that we're interested in, thousands or hundreds of thousands. People are now aligning billions, aligning whole genomes. But doing it straightforward like that is out of the question. So, in fact, let me digress here and start talking about how many alignments there are, just for a couple of reasons. One, to drive home this point that straight enumeration is not going to work. I want to make that point really clear because we're going to spend a lot of time on another method that's much more efficient. And then you ought to ask, why are we doing that? Why are we going to spend so much time on something else when there's clearly a very simple way of doing it? And the answer is the simple way just doesn't work in practice. And the other way of doing things, which is an example of what's called dynamic programming, is a method that permeates bioinformatics. So we want to see how it works on this particular example, and then we'll see how it differs in different examples. But the reason for going to something clever that's going to take us a couple of lectures or more to fully develop is because the straightforward approach is not practical. So I want to show you that. The other reason for counting, in particular here, actually several reasons, is it's going to remind you a little bit about permutations and combinations, which is something that you'll need throughout the quarter. And the third reason is that I have a couple of Perl programs that I'll put on the web that do the counting. And that will be a way in which you'll start seeing some Perl program in action. So, how many alignments are there of 2 sequences? Let's make them both the same length to begin with. That'll simplify things. And later, if it might be appropriate for me to ask you as a homework type question to modify this formula for 2 sequences that are not the same length. But 2 sequences of length, let's just abstractly call it n each. Okay? Anybody have an answer? No, that's okay. That's to be expected. All right. Well, the way we're going to do this analysis, there's our question. We're actually going to focus on how many spaces are inserted. So we're going to abstractly say, let's say the number of spaces inserted is r. Just have a particular symbol for it. We'll figure out how many alignments there are when there are spaces, and then we'll just sum over the possible values of r, and that will be our formula. Okay. So here's a subproblem. if we insert R spaces exactly into each sequence, how many alignments are there? Okay. Oh, by the way, Sasha's in the lab today after class, so those of you who want help today in the lab, this would be a good time to go over there. So, in order to answer this question, let's just imagine that I'm going to put down placeholders for sequence S1 after I've put in spaces somewhere. So how many placeholders are there? Oh, okay, there are 10 in this, I guess, in this little example. This is designed to get your intuition moving. Usually, when you do mathematics, this is sort of the picture that you use to get your intuition going. But so this is abstract. How many spaces are there in terms of our notation? We have n original characters, we have r spaces, so n plus r. Okay. Places. Okay. So now, if you focus on putting the spaces into S1, okay, now that we have actually the placeholders, what that really means is putting in the n characters from S1 into these placeholders. We have n plus r placeholders now. And if I look at where the spaces went into S1, it really means, well, okay, I'll put the first character there, and I'll put the second character there, and the third character there, and the fourth character there, and so on, of S1. And then that gives you what spaces you've put in what and where you put spaces into S1, which is 1/2 of the description of an alignment. Okay? So we're trying to count how many alignments are there, and the way we're thinking about it is by saying, I'm going to generate an alignment by looking at n plus r places and now putting into those places the n characters of S1. And how many ways can I do that? So step 1, put the n characters of S1 into the n plus r placeholders. Okay. In how many ways? So this is where the permutations, combinations stuff, high school, and in your statistics course comes in.
C n plus r combination.
It's what?
C n plus r, I think.
Yeah, okay. So it is, there are different ways of writing this. N plus r, choose n. Okay? That's one notation. You have n plus r places, and you can choose n of them to put in the characters from S1. And this is the number of ways that you can do that. It's sometimes also written this way. Okay, C, n plus r, comma n. It's written this way in older textbooks where they didn't have nice typesetting. This was difficult to write out in the book, so this is the another way which is often written. And what's the formula for that? What is this? N plus r, choose n. I know there's some students who are in statistics. I mean, grad students in statistics. It's got to be second nature to you, and some math students too. It's awesome.
Anyway, n plus r explanation mark over n plus r minus n plus n.
You were getting there, but you would have simplified it. You were going to make it n plus r minus n factorial, but that's the same as r factorial. So, and what's factorial, by the way? So k factorial is the 1 times 2 times 3 all the way up to k. It's the product of those. Okay? So this is a big number. N plus r factorial is a big number. Of course, you're dividing by the product of things that look pretty big too. But this is a very rapidly growing function. In fact, if you just to see how bad this might be, just make r about half n. About n, sorry. So then you have 2n, choose n. And if we had time, this should be something like n to the n. Okay, it's not quite right, but this is very rapidly growing. Okay, probably even faster than that. But it's maybe n over 2. But anyway, very rapidly growing function. Okay. Now, of course, we're dividing. Sorry, that's what this is. All right, so that's one part of this analysis. We're putting in characters from S1. Now, in step 2, we're going to put in the characters from S2 in here in order to get an alignment. So, how many different ways are there to do that? Is what? Okay, the first thought is it's the same thing. Okay, but it isn't really. Right, because we're not permitted to put a space opposite a space. Okay, so you might think, oh yes, S2, we're just going to put its characters in there somewhere, and then the total number therefore will be the product of these two things, or this thing squared. But we said we're not going to permit a space opposite a space. Okay, so now how do we think about this? So you want step 2. In this many ways, okay. So step 2, put in characters of S2, but avoid a resulting space opposite a space. don't have one space opposite another one. So if this is where I put in characters, I have to be sure not to put any spaces here. This has to be a real character. Okay? So maybe you see the logic of how you think about that. Well, you sort of think the opposite. You stand on your head. In S1, when we were thinking about S1, we were thinking about where we're going to put the characters of S1 into here. We could have equivalently thought about where we're going to put the spaces. Okay? And now, when we're down here, we want to make sure that we don't put spaces opposite a space. So one way to think about this is where will I put the spaces that are in S2? They all have to, if they're not going to be opposite a space, they have to be opposite a real character. Okay? So if I take the n spaces in here, the n positions in here that were used for real characters, and I now choose where I'm going to put spaces, where I'm going to put the R spaces down here, then that will tell me where the spaces for this one are, and then the opposite, the ones that were not chosen as spaces are chosen for characters, and then I'll put those on. So let me remind you, this is n plus r, choose n ways. And what I just outlined is that you have n real characters there, and we have to decide where we're going to put the spaces. There are spaces ways. Okay? Now, so hopefully you get that logic, because it's a kind of a cute idea, a cute thought, that in order to avoid putting a space opposite a space, if I already know where the characters of S1 are, I just have to think about where I'm going to put the spaces from S2, and only choose places where there's a real character already from S1. And I can do it in that many ways. And having chosen where the spaces are, I, of course, then just go along with the characters of S2 and stick them in those positions that are remaining. Okay? So, the total equals n plus r, choose n, times n, choose r. Okay? For r spaces. Now the first question you might ask, by the way, is what happens if r is bigger than n? I mean, n is not bigger than n plus r, so this is well defined. But what does it mean to choose more spaces than there are positions? Well, you can't do that without creating a space opposite a space. So in fact, r is always less than or equal to n. So we're only interested in r less than or equal to n, so this makes sense. So now the total number of alignments, that was the total if you use r. So total number of alignments equals the summation of r, 0 to n plus r, choose n, times n choose r. So we'll try to do some analysis on this to convince you that this grows very, very rapidly. And I'll put on the rapid program that computes this, actually two programs, one that computes this in a very poor way and runs out of memory quickly, or is unable to get to large n, and another one that does it a little more efficiently and gets to very large n. You can just see that these numbers grow very, very rapidly, so that there's no possibility of working with a program that generates all the alignments. We're going to have a more clever way of doing things. And that's why the need for that, and the fact that we can do that, is why this course is in computer science. Well, at least that's what I focus on. Yes, one question before we have to go.
Is it for each way, the order of the characters now? You have n choose, say you have n plus r, n choose ways. Each way doesn't matter what position each one goes to the other. Like you're putting in like 4 or 5 characters, right?
Yeah.
This doesn't matter what order the characters.
Well, the characters have to, okay, so the question doesn't matter what order the characters are. The order of the characters are the same as they were in S1 and S2. To make an alignment, we just are permitted to put in spaces. We're not permitted to move around characters. Later we may be in a richer model, but right now, our model of alignment and of molecular evolution does not permit that. So last time, we gave a precise definition of what an alignment is between two sequences. We gave a precise definition, although a fairly simple one, of what we mean by two sequences being similar. And I remind you that it ended up as an optimization question of two sequences S1 and S2 was defined as the maximum value you can possibly get, the maximum over all alignments of S1 and S2. Over all possible alignments of these two, you wanted to maximize the number of matches that resulted, minus the number of mismatches, minus the number of spaces. And this value, the largest number that you can possibly get over all alignments of S1 and S2, was defined as the similarity or similarity value of S1 and S2. And so it gives you a way of, a numerical way of talking about how similar two sequences are. And associated with that value is an actual alignment, which shows you the relationship between S1 and S2 that has that value. Okay, the next thing we did last time was to ask how many alignments are there? Because if there aren't very many, then you can write a very straightforward computer program that generates all of them and calculates this number, and then just takes the largest over all of those. Ultimately, we want a method, and it has to be efficient. It has to be something we can actually use in practice that will calculate this number. And what I was pointing out last time is the number of alignments is much too large for a straightforward approach, a complete enumeration approach, to be practical. It's totally out of the question. And in fact, one of the things you have on your homework this week is to run a program, 2 programs actually, that calculate the number of alignments. And you'll see how rapidly that grows. And in the class notes that I put on the web from last lecture, I actually have a kind of approximation. Last time I gave you an exact formula. But you can approximate what its value is, and you'll see that it has exponential growth, very rapid, explosive growth, as the lengths of the strings increase, and lengths of the sequences increase. And you can see some of those first values, what their actual numbers are with the programs that are available on the web. So I'm not going to say anything more about this, except to say that any approach based on enumerating all the alignments is totally impractical. Now, what I really should do at this point is start talking about how we efficiently compute this without complete enumeration. And I may get to that today as well. But because the lab, we have this synchronization problem with the labs, the lab started on the very first day of class, so it's slightly running ahead of the lectures. I want to say enough today about things that are related to the lab that you can actually jump into the lab. So I'm going to skip over this topic of how to compute this one and do this slightly out of order and talk about richer models right now. Just something that would otherwise come later. Because this week's exercise involving XCorral is to explore different models and explore different parameters of different models to see which ones give you alignments that seem to have biological meaning. And the way we're getting at that is in two different exercises where we have the alignment that's believed to be right, believed by the appropriate biologist to be the alignment that exposes the biological meaning. In one case, that alignment came from crystallographic studies. You have two proteins, you know what their three-dimensional structure is, and then you can do some kind of superposition of those three-dimensional structures, and that implies an alignment of the sequences. Places where the structures line up pretty well, are places where you want the alignment to line up pretty well as well. And certain properties, secondary structure, the alpha and beta structures of those proteins, you'd like those to line up properly as well. So in the Barton data, you start with an alignment that's believed to be correct. You input those sequences to XCorral without the alignment, and then you see what combinations of models and parameters gives you back the alignment that Barton thought was right. And what's most instructive also is to see that with many other choices, and there's lots of other choices, you get alignments that are really crummy. And that should be kind of a warning in general about how to use this technology. The other thing that you get when the parameters are wrong, the model is wrong, is you get lots of equally good alignments. Alignments that the system, in terms of this objective function, you see, ties are possible. There's nothing in this that says there's only one alignment that gives you this biggest value. There certainly could be more than one alignment that does that. And if you have a set of parameters where you get thousands or tens of thousands of alignments that give you all the same largest value, then this is not a technology that's going to be of great use. How do you know which one of those alignments is the one you want to run with? So that's another thing that you're exploring in XCorral. And if you get lots of polygons, that's probably not a good thing. In fact, what I'm doing now is I'm telling you the answers to the questions on this week's lab, but you have to connect the answer to the question properly and make that make sense. And I'm going to show you a little bit more about XCorral in a minute. So, richer models. So how do we want to enrich this model? The first thing, actually, and this relates to the second exercise, in the early 1980s, this was sort of the model people were playing with, alignments under this objective function. But they started differentially weighting mismatches and spaces. So that's modeled by putting a multiplier x and a multiplier y here, and then saying, well, I think x should be a half, and I think y should be 12 or whatever. Now, of course, the case that we've looked at so far, x and y are just equal to 1. But if you think that mismatches happen more frequently in nature than spaces do, then maybe you should make this y bigger than x. You should put a higher penalty for having spaces so that the alignment that gives you this maximum value is one that has fewer spaces and maybe more mismatches. Okay, so having these multipliers, then you have to argue what the proper multiplier is. So that's the first way in which people enrich the models. Multipliers on mismatch and space penalties. Okay? You might ask why I don't put something on matches here, right? X, Y, Z. Why don't I play around with the value of a match? What's the answer to that? Yeah, you can conceptually think about saying, yes, this is really a parameter here, here's a parameter, there are really 3 parameters. But for any choices of x, y, and z, if I just divide here by z, then this one goes back to being 1. This is x over z. This is y over z. And that's just a different, since I'm going to let this parameter run through its all possible ranges, it really doesn't matter whether I call it x divided by z or just call it x. Okay. So another less clumsy way of saying this is there are really only 2 independent parameters here. If I have 3, I can think conceptually having 3, but there's only 2 that are independent. I get the full range of behavior by setting this to 1 anyway. And then from a practical standpoint, it's good to only have 2 parameters because on a computer screen you only have 2 dimensions. There are actually programs that will show this kind of thing in 3 dimensions, or this 3-dimensional representation, but you don't need to when you only have matches, mismatches, and spaces. 2 parameters are enough. Okay, so multipliers on mismatch. That's another way people got to richer models that hopefully found alignments that were more meaningful from a biological standpoint. And part of your exercise this week has you playing around with this model, okay, without any further embellishments. did in the 1980s somewhere is there wasn't a lot of data then, but he had two fairly short sequences where he felt that he knew what the right alignment was. I mean, an alignment that meant something biologically. And he wanted to see how good is this technology, this alignment business that people were all starting to do. And now we just do massively. And what he did was he took his example, his two sequences. Let me just clean this up a little bit. Number of mismatches minus number of spaces. And he multiplied by x, multiplied by y. And by hand, he did what XParal does now automatically. He computed this nice decomposition of XY space, where he could see all of the possible alignments, all of the alignments that maximized this objective function over all choices of x and y. So whenever you fix a particular value of x and y, then you have a specific optimization question, and you can find through the method I haven't told you about, but you can find the alignment that maximizes that objective. And he did that for all x and y in a systematic way that XParal now does automatically. And he looked at all those alignments, and he found that none of them were really satisfactory in terms of capturing the alignment that he thought was right, that he thought was biologically relevant. And that led him, and others, he wasn't the only person, into this notion of gaps. So that's the second way that the model is enriched, particularly for protein. Okay, so what is a gap? Here's a definition. A gap is a contiguous sequence or interval of spaces. Okay, so if I have, let's say, A against A, and then three spaces here, B, X, Y, Z, Z, W, P. Okay. This is an alignment that has however many matches it has, however many mismatches it has, but it has 1, 2, 3, 4, 5, 6 spaces, and only 4 gaps. Oh, sorry, 3 gaps. So the 6 spaces are organized into 3 gaps. And 1 gap here, 1 gap here, even though there's just a single space, it's nonetheless a gap. And here's a longer gap. So you can have different alignments that have exactly the same number of matches, mismatches, and spaces, but with different numbers of gaps. The spaces are organized into different number of gaps. The way they're organized into intervals can differ. And what he was asserting, particularly in protein, is that an alignment that sprinkles the spaces all over the place doesn't look very real. Doesn't reflect the biology that he knows. Doesn't reflect how two sequences that are related to each other by biological processes ought to look when you do the best possible alignment. In his view, they should have just a few gaps. They may be very long, or they may be very short, but the spaces should typically be organized into runs or intervals of gaps. So he then, remember, he looked at this objective function in completion. So I'm moving back over here now if you want to. Thank you. He looked at this model. This is a model. This is a mathematical model associated with an algorithmic problem. But it has no notion of a gap in there. Even though it has x and y, it has no notion of a gap. It can multiply mismatches in spaces, so he has a way of fine-tuning that. But even with all the fine-tuning that he did, he couldn't get an alignment that recreated the alignment that he thought was meaningful. And so he and others at that point introduced into the objective function this further term, which is subtract off something for gaps. Okay? You don't want to have a lot of gaps. So we're trying to maximize, we're trying to make this big. You want a lot of matches. You don't really want a lot of mismatches. You don't really want a lot of spaces. But you'd also like to control how many gaps you have. Okay? And he was, at the time, wearing that T-shirt. Would you stand up and, yes. You know what T-shirt you're wearing. And face the camera. And anyway, the camera should capture that one. I guess the camera's not listening. Anyway, he thought it was important to mind the gap. Which is what that T-shirt says. And how many people know where that comes from, by the way? Just an odd question. Only 1 or 2? Yeah, it comes from the underground in London, where they have it as you get off the train. It's stenciled there almost every exit, so you don't fall through or fall too far. Anyway, they make those T-shirts everywhere. So if you ever pick up one. So anyway, they introduced the notion of gaps. So you don't want to have a lot of gaps, and you can control things to some extent by including this in here. Well, the next obvious step is gaps and a multiplier on the number of gaps. So now we have x, y, and z. How do I get my y inside there? That was silly. Y times the number of spaces. So z times the number of gaps. So now that we have 4 elements of an objective function with matches, mismatches, spaces, and gaps, now we do have 3 independent variables. And we would like to have a multiplier x, y, and z. And that's why some parametric programs actually would like to display this in 3 dimensions, showing the axes for x, y, and z. XParal only shows things in 2 dimensions, and you have in your menu your choices. You have to decide which 2 out of these 4 you're going to parameterize. Okay. So what Fitch next did is he parameterized these two, I believe. But you can see in the notes, Y and Z. And just forget X because that used to go there. And by playing with Y and Z, and for each setting of Y and Z finding the best alignment, the alignment that maximizes the subjective function, he was able to find an alignment that recreated the alignment that he thought was right. And so in your homework, in your exercise this week, you should be able to do that as well. And the same thing with the Barton data. That's more complex. It's a much longer sequence, but you should be able, after failing to recreate the alignment that Barton starts with, or by many settings and different models that seem to give you too many choices, and so on, you should eventually, with the right model, be able to get an alignment that seems right in comparison to the Barton's alignment. Okay, and actually for the Barton, there's a third very important element that makes richer models, and that is substitution. Substitution, I forget what we call it in XPRL, but generally we call these substitution matrices. I think in XPRL it's called something else. But anyway. So with substitution matrices, I mentioned this briefly today in lab, and we'll talk about this more throughout the quarter because it's a question of where do these things come from? How do you get good substitution matrices? But what this is saying is that not all mismatches, and in fact not all matches, are of equal significance. So a mismatch in alignment that matches, for example, isoleucine to leucine is not a huge, you don't have to invent a huge, difficult biological story for how that happened. You can still imagine the two sequences where they have this kind of a mismatch are highly related because these are two amino acids that are quite similar and that mutate one to the other fairly easily. And therefore, this kind of mismatch should be less penalized. Than a mismatch, say, of tyrosine. Is this tyrosine? And glycine is a Y, okay. And what's a G? Glycine. So this is big and this is small. And there are other ways that you can find two amino acids. One's charged, one's not, and so on. Hydrophobic, etc. Two that are quite different, where a mismatch between those is postulating a large chemical and biological change, and therefore probably should be penalized much more than this kind of a mutation. And so what you have are substitution matrices that encode all of those. So you just have, this is particularly true for amino acids, but it's also true in terms of DNA as well. So you have all of the amino acids and so on, the 20 here, and 20 here. These are the identities along here. And some value for particular mismatches that will be found in this matrix. Okay? And even some value for matches that are found in the matrix. Now, generally, the values for matches are going to be positive, and the values for mismatches are going to be negative. I should have told you exactly how this is used. When you have an alignment, the score you give for that alignment is no longer just the number of matches. It doesn't start out just with the number of matches, but it is the score that's taken from the summation of the values that are taken from this matrix corresponding to the matches that you actually have in there. So over here, well, this is not an amino acid because B is not, and maybe there's some other ways in which this is, anyway, just imagine it was. So you have a match of A to A, and you go into the substitution matrix and you'd say, you find out what value does an A match have. So that contributes to the value for the match, what do you get from a Z, what do you get from a P, and so on. And those are taken from that particular substitution matrix. And then mismatches, you would also go into the substitution matrix and you find the QR value. And that would then be taken, if the mismatches are negative, that's actually as a plus. And in fact, if you look at XPRL, one of the windows, the objective function windows, has number of matches plus number of mismatches. And that has a subtraction for spaces. And I think I mumbled something in notes about how that's kind of an error. But really what it is just, it reflects the fact that the values for mismatches in the matrices are already negative. And so we're really just, from an arithmetic standpoint, we are adding those. We don't want to subtract a negative because then it'll become positive. But the spaces still are subtracted off. Okay, so the substitution matrices are very, very critical in terms of getting the right alignments, getting alignments that are biologically meaningful. And again, this week's exercise is to get you to sort of discover how important all of the pieces of the model are in order to get a good alignment, a biologically meaningful alignment. There are many substitution matrices that have been proposed out there. The one that you're using in the exercise is something called PAM 250 plus 8. And it's in a file that's in the directory that you're working in. You can actually just look at that file and you will see what the values are. You have the two coordinates on that array that's in there, and you can see what the values are. Now, the PAM matrices we'll talk about later, how they were constructed. It's a whole series of matrices, and this sort of indicates which PAM matrix it is. The plus 8 means they took the original PAM matrix and they added 8 to all values. A little bit of alchemy. But today, and PAM 250 used to be the default matrix that a lot of people would use when they didn't know any other one that was better. Today, this is a little bit dated. And people tend to use the Blossom series of matrices, which we'll talk about also later in the quarter, where these things come from. But I don't have that built in. You can use it. I'll make it available. And in XParal, when it asks for what scoring matrix, there's an option for other. And as long as you have it in that directory in the right form, you can use it. So you can try that out if you like. Blossom 62, I think, is now sort of the default. When you don't have anything else to use, people tend to use that one. And we'll talk more about these. I just want to say that, particularly for protein comparisons, DNA is somewhat different. But for protein comparisons, all of these features of the model are really have ended up being critical in terms of reliably getting back good alignments. And probably the most important are in opposite order here from the way I've done it. The substitution matrix is really important. Gaps in the model tend to be significant, very important. And then the actual multipliers more fine-tune things. Now let me just tell you some terminology and then I'll tell you the although. When we're looking at protein under this model, gaps, the gap Z is oftentimes called the gap initiation cost. Okay, and you'll see that referred to in the XParal notes, and you'll see that in biological literature. So that is what it costs you for a gap. So if you think about starting a gap, and you don't know how long it's going to be, but there's going to be a gap, then you can think about initiating a gap without knowing how long it is. Okay, so that's why it's called the gap initiation. What you pay for a single gap is Z here, and whatever you set Z to is the specific gap initiation. And then Y is referred to as gap extension cost, or penalty, cost penalty. Extension cost. Okay? And again, if you think about this, when you start a gap, you have to pay to start it, but you don't know how long it is. Every time you add a space to it, you're extending it. And you have to pay Y for each one of those spaces. So that's called gap extension. Okay? I think it's simpler just to say there's a cost for the spaces and a cost for the gap. But historically, those two terms have come up, gap extension for spaces and gap initiation for cost. Now, the although is that even though people don't always play around with Y and Z the way XParal allows you to, there are definitely beliefs about the rule of thumb out there for how Y and Z ought to relate to each other. And some of these have become almost gospel. But if you go back to where the advised value of Y and Z came from, in many cases it came from somebody off the top of their head. They said, let's try Y of 1 and Z of 12. Something like that. And then it gets written down on some paper that those are the right two values. And then it becomes part of somebody's program and the manual that's associated with that program. And pretty soon as though there was some real deep analysis that gave you that. So generally, the gap initiation should be more expensive. It should be more difficult to start a gap than to extend it. And actually, the 12 to 1 is actually some default values for some alignment systems that are out there. But in XParal, you don't have to rely on that just single choice. You get to play around with what you think Y and Z ought to be. And in comparing proteins, these tend to be the two parameters to play with. What you have on spaces and what you have on gaps. Okay? So I want to show you a little bit more now about XParal specifically. This whole business is called parametric alignment because we have parameters on portions of the model. Now, how well is that coming out in the TV version? Can you make that fill the whole space? See, I noticed that. And try to play whatever you can so this is most visible on the TV screen. Thank you. Okay, so here's my the objective function. We're trying to maximize the value of the matches. And I say value now because that is implying we're taking the summed value from some substitution matrix. Okay, minus the value of the mismatches. Well, again, whether this is a plus or minus really depends on what's the actual shape of the what the value is in the substitution matrix. But you should all understand that mismatches are bad and somehow they should be penalized. Whether the value in the substitution matrix is written there negative, in which case you add here, or whether it's in there positive, in which case you subtract. You just have to be careful about what you're doing. Minus the number of spaces. When I have a multiplier alpha, well, that used to, over here that was a y. Okay, now it became alpha. We all speak Greek now. Minus beta times the number of gaps. Okay? And so we have two parameters, and that gives us a alpha beta space for our choice of what alpha should be and what beta should be. The default in some systems has alpha of 1 and beta of 12, but in XParal, you get to explore the entire range of values in these two parameters in order to see what's the consequence of setting the values differently. And what you get out of XParal is you get a decomposition of the alpha-beta space into these regions, which are called convex polygons. And you can prove, that's not something we're going to do in this class, but one can prove that this decomposition has the following property, that whenever you pick a value for alpha and beta inside of a particular polygon, no matter what choices you make for alpha and beta, if they fall within the same polygon, then the same set of alignments are optimal for either point. I'm saying that's slightly different. If I pick this point, for example, right here, and I find an optimal alignment for that choice of alpha and beta, the same alignment will be optimal for that choice of alpha and beta. There may be ties, there may be more than one alignment that's optimal at this point, but that other one, all of them that are optimal over here will be optimal over there. And by optimal, I mean they maximize. They make this maximization function as big as possible. So the polygon, inside of a polygon, it doesn't really matter what your choice of alpha and beta is. You're going to get back from the alignment algorithms. The alignment that maximizes the objective function will be the same one anywhere in here. Also, the converse is true. That outside of that polygon, no alignment that's optimal for a point inside the polygon will be optimal anywhere outside the polygon. Okay? So if I pick an alpha and beta here, and I find an alignment that maximized the objective function for that alpha beta, I know for sure that that one will not be optimal over there in any other polygon. Okay? So what this decomposition shows you is exactly where the values of alpha and beta cause a real change. Okay? Inside one single polygon, you have a collection of alignments that are optimal. They're optimal nowhere else. And so this decomposition tells you how the optimal alignments behave as a function of alpha and beta. That's what XPRL does for you. Now, let me show you an actual picture. This actually is a little bit, this one is taken from a earlier version of XPRL. So what's up on all the choices up on the top are not quite the same as what you're going to have in your exercise, but all the important ones are there. And this is actually the final decomposition that you should end up seeing. And let me look for the Barton data. And let me show you the most important places to look. One of them is right here. And you can see that, there's one polygon that's shaded. And the alignment that's associated with the shaded polygon is showing up in the alignment window. So we're seeing up there an alignment has got some, notice an alignment has got some spaces in it, it's got some gaps in it. And here in this window that says VAR, it tells you how many matches that alignment has. If you can read this, it's 29. 29 matches. The next one is how many mismatches, that's 73. The next one is how many spaces, it's 16. And the next one is how many gaps, that's 5. Okay? So in the alignment that's shown, which is optimal somewhere, it's optimal everywhere inside this polygon, you have those features, 29 matches, yeah.
You said all the interior points within a polygon are as optimal as the other ones. So what about the lines?
Okay, so the question is, what I said was that for any alpha beta point or xy point inside of the polygon, any two of them, the same alignment is optimal at one point will be optimal at the other point. And the question is what happens along a border between two polygons. There, all of the alignments that are optimal in the interior here, and all of the alignments that are optimal in the interior on the other bordering polygon are both optimal along this border. And similarly at a point, that's the intersection of more than two polygons, all of the alignments that are optimal in the interior of the polygons are optimal at that point. So you have a lot of different co-optimal alignments. Okay, so when you look at an XPRL display, you want to see what optimization did you choose. This is one that's called n-gaps free. I haven't explained to you. I should tell you what the terminology is. What we've seen so far, those alignments are called global alignments. Global because every character in the two sequences participates in giving the value to the alignment. Sometimes there's a belief that gaps that are at the ends of the alignments should not be scored. If you have one sequence much, much smaller than another sequence, for example, you're going to have very big gaps, probably, at the ends. And those are not necessarily meaningful. So there's a variant called n-gaps free. And XPRL gives you several choices. Another one's called local alignment, which we'll look at a lot in this class. At any rate, you'll see in your lab notes which variant to use. But here's where it shows what variant you're using. This shows numbers, matches, etc. of the alignments that are in this polygon. Over here, what this shows is, remember, the Barton data, you input aligned data. You input aligned sequences. In the file, you can look at that file, the Barton Go file. The two sequences are actually there as an alignment. There are spaces in them. That's the alignment that Barton thought was the right one from the basis of crystallographic studies. So we know how many matches, mismatches, spaces, and gaps that alignment has. So what's shown over here is the number of matches, mismatches, indels, and gaps that alignment has. It turns out that one in the Barton data has 30 matches, 72 mismatches, 16 spaces, and 7 gaps. Okay? The alignment we're seeing over here has 29 matches instead of 30, has 72 mismatches instead of 72, has 16 spaces, which is the same, and is organized into 5 gaps, whereas it's organized into 7. The alignments that are in here may not be the closest one, the most similar one to what was input here. In the current version, not in this one here, but in the one that you're playing with, there's actually a button that says, find the one that's closest. Forget about showing you the full decomposition. It just works until it finds one that it knows is the closest, and it stops there. But you can always sort of compare that's shown here compares to what was input, if you have an input alignment. In the Fitch case, you're going to type in the sequences, there's no alignment given. Then what's down here actually tells you some numerical differences between the alignment at hand here and the input alignment. It says at point x, y, and I'm not going to tell you how it picks which points to look at, but at point x of 0 and y of 5, it picks a particular point. The value of the alignment shown up here, which is in here, well, this 0, 5 should be inside 0, 5. Yeah, sorry, 0 is x, and 5 is along here. 0, 5 should be in there. At that point, the value of the alignment that's shown up there is 941. But the value of the input alignment is 932, which is a numerical difference of 9, which is like 1%. Okay, so that's another reflection of the closeness of these two alignments, that this is a very small percentage difference between the two. Now, another thing that we have in the current version of XPRL, it's not in this slide, is something that's up here, which shows you the number of equally good alignments in each polygon. So, in this polygon, I vaguely remember there's either only one alignment that gives you the maximum value. It's optimal at every point inside here, but there's only one of them, or it's 18, I don't remember which. Some of these in here vary between 1 and 18. Okay, and then these buttons up here say next and previous, and you can scroll through the alignments. Sometimes the changes are quite subtle, but you can show the different alignments that are called co-optimal. And if there are more than 10,000 of them, it just says more than 10,000. And part of your homework exercise is to think about what does it mean if you've picked a model and a choice of weights where you're in a polygon with 10,000 equally good alignments. What does that mean about the value of this alignment as a tool to find biologically meaningful alignments? If there are 10,000 that are equally good under the criteria that you're working with, it's not a very precise tool. If you have only one, maybe the wrong alignment, but at least it's only giving you a few choices. Similarly, the question of how many polygons there are is the same issue. If there are too many polygons, then there's too much to explore. And then you can be a little more precise. If there are 18 in here, you can ask how do they really differ? Talking about computing the similarity of S1 and S2, two sequences. And remember the definition. We defined alignment. We've seen many alignments now. It's the max over all alignments of S1 and S2. Max of... Now we're going to go back, for the purposes of beginning to understand how we compute similarity, we're going to go back to our simplest definition, even though last time we were talking about all the ways that are important in biology to make that definition more relevant. Maximum number of matches minus the number of mismatches minus the number of spaces, or indels. Okay? So this is our objective function. We want to find an alignment that maximizes this sum. And there are so many alignments that it's absolutely out of the question to have a method that would simply enumerate, look at all the different alignments, and calculate this value for each one. So we need an efficient method, a very efficient method. What does efficiency mean? Of course, it means, generally speaking, that it runs quickly, or that it doesn't consume a lot of computer memory, because that might be something else that isn't available. But certainly, time is important, or speed is important, and secondarily, memory, computer memory. Now, if we're talking about speed, first of all, you have to realize that the time that a program or an algorithm takes to compute something, to compute the alignment, the best alignment, or the similarity value, is probably going to increase as the size of the sequences, the size of the strings increase. Huge strings, it just seems intuitive, are going to take much longer to do those alignments than short ones. So when we talk about speed or efficiency, we're always going to talk about as a function of string length or size. And just as we computed, when we calculated the number of alignments, we just assumed that both of the sequences were going to be of the same length. We called them n. So now, we had a variable. We didn't talk about how many alignments are there when the two strings are of length 10, or so on. Well, that's what you can compute by the program that's available on the web. We had a parameter for those two strings. So one is length n, and the other one is length m. And they may both be the same in some of our discussions if we want to simplify things a little bit. But anyway, we have abstractly two lengths, n and m. And we realized that as n and m increase, certainly one could expect that the speed is going to, the time is going to take longer. It's going to be longer. The time's going to be longer, that's true. It's going to take more time, okay, as n and m increase. All right. But how do we actually clock that? Do we want to sit there with a real watch and talk about wall time? Well, that certainly is going to be dependent on what computer you actually run on, or other aspects of the computing system. So we want to be more abstract because we don't want to say, on your PC, Pentium 2 is going to take this much time as a function of NM, and on some other machine it's going to be something else. So what we look at is we use number of operations needed to compute similarity as a function of N and M. Okay, so that's how we're going to clock. That's how we're going to talk about whether a particular method is fast or slow. How many actual operations does the algorithm use to compute the similarity as a function of N and M? And what do we mean by operations? Well, that will depend on the particular algorithm. Sometimes it's additions, arithmetic operations, or comparison operations, or looking up a particular number in memory operations, things of that sort. All right, all this will become clearer in a moment in this lecture, I hope. All right, now, okay, so that's what we're going to do today, is begin to talk about how we're going to compute similarity very efficiently. Now, it turns out that in all these discussions of algorithms and of alignment generally, it's very useful to use what's called an alignment graph. And alignment graph is really a very simple object, and I happen to have one here.